right, let's get started. So it's my great pleasure to introduce our main tutorial speaker, Ann Hermundstad. She's currently a group leader at John Elia. She did her PhD in UC Santa Barbara in physics, and she did her postdoc with Vijay Balasubramanian. And today she's going to give us a very long tutorial, on normative modeling, which is super cool. And although I am not fully subscribed to the normative modeling camp, normative modeling is indeed very attractive, and it gives very, very nice stories. So very important to learn normative models. All right.
Awesome. All right. Thanks, Memming, very much. Thank you all for being here. I'm really excited to talk to you today about normative approaches in the context of both sensory coding and behavior. So I'm going to break up the afternoon into a couple different chunks. So for the first part of the afternoon, I'm going to talk about introduce normative approaches and talk about them in different contexts. And then in the second part of the afternoon, we're going to work on a problem set, sort of get hands-on experience working with these types of approaches. And then we'll come back at the end to go over this problem set and sort of give some outlook. So for the first hour or so, I'll spend introducing the normative approach and talk about this in the context of sensory coding. Then we'll break for a little bit, come back for the second part of the lecture where I'll talk about normative approaches in the context of inference and action selection. Then we'll break for the problem set and then close. So you should all at your table have worksheets. There should be enough for everyone at your table, but if you don't have them, during the breaks, just come and find one of us and we will make sure that you get one of those. We'll be using that in this problem set later on. Okay, the Wi-Fi password is up here in case anyone hasn't gotten it already. So you can use this to access the problem set later in the session. All right, we have a group of 12 fantastic TAs who are here to help today. So I'd ask that each of them stands up. Diego, Zoe, Pierre-Etienne, Carolina, Anna, great, Maz, it's very hard for me to see up here, Jorge, Josue, Marcella, Sashank, Satpreet, and Charlene. Okay, great. So they will be here to help if you have any questions during the breaks, and especially during the problem set later on. Okay, so let's dive right in. Before diving into the normative approach, I think it's useful to step back and reflect a bit on the state of systems neuroscience today. So we are at a point in time where it's possible to simultaneously record from very large populations of neurons in the brains of awake behaving animals, and in parallel reconstruct anatomical and physiological details of the circuits that support these activity patterns. And so as a field, we are collecting tons and tons of data. And so we've seen an explosion of tools coming from machine learning and data science that help us extract patterns from this data. And the idea here is that the data can reveal itself to us. We can ask the data sort of to reveal what's in it to us. And so this has been a very powerful approach. But I would argue that we're also in desperate need of general principles that can help us understand why we might see particular patterns that we see in the data, and how the patterns that we might see in one system might relate to the patterns that we see in another system. And so this is where I think the normative approach can provide a complementary perspective. So one of my favorite quotes that captures some of this essence is the following quote, and some of you may know this, but I'm going to read it anyway. It says, "A wing would be a most mystifying structure if one did not know that birds flew. One might observe that it could be extended a considerable distance, that it had a smooth covering of feathers with conspicuous markings, that it was operated by powerful muscles, and that strength and lightness were prominent features of its construction. These are important facts, but by themselves, they do not tell us that birds fly. Yet without knowing this, and without understanding something of the principles of flight, a more detailed examination of the wing itself would probably be unrewarding." So this is a quote from Horace Barlow from his 1961 paper that in part laid the foundation for the framework of efficient coding, which is one of the normative frameworks that we're going to be talking about today. So if I were to put this quote into today's context, I would say that we are collecting a huge number of facts many of which are likely important. But to understand which facts are important and why, we need to understand these facts in the context of the functions that a circuit or an animal might need to perform. And I don't think this is a particularly controversial statement. But the type of approach that Barlow is advocating for here is one in which we start with a function, here flight, and the context in which that function needs to be performed, the physical world in which we live, which is governed by certain physical laws. And we think about the system that best performs this particular function in this particular context. And this is what we would call the normative approach. So starting or postulating a function and a particular context in which that function needs to be performed, and then trying to identify the optimal solution for solving that particular function. And this is in contrast to an approach where you might start by measuring the properties of the wings and then trying to deduce functionality from those measurements. Both of these approaches are widely used in neuroscience. Both are incredibly useful. Today, I just want to focus on this approach that Barlow is in part advocating for here. Okay, so to sort of transition this into the realm of neuroscience, I like to start by giving some examples from a system that I think we all have pretty good intuition for, and that's our own visual system. So our visual systems are incredibly powerful. They allow us to very quickly parse our surroundings. So when you came into this room, perhaps for the first time, you were able to navigate to find a chair. You were able to tell that the chairs look sturdy enough to sit on. If we were to have to run out of this room, all of a sudden, you could find 6 or 7 different routes from where you're sitting towards the door. And you could do this all just by looking at the scene around you. So in part, this speaks to the power of our own visual systems, but it also tells us something about the world in which we live. The reason we can differentiate a chair from a table is because they have different physical properties, and these are relayed to our eyes through different statistical signals, different patterns of light. And so we can start to understand how the statistical regularities in the world around us impact our own perception of the world by dialing these sorts of regularities into an otherwise random setting. So if we take this random white noise image here, and we start to dial in certain patterns, we can ask, what sorts of patterns do we have to dial in, and how much do we have to dial them in before you can start to make sense of what it is that you're seeing? So I want you to raise your hand when you think you see something that's non-random, and I want you to raise both hands when you think you know what that non-random thing is. Okay. Ooh, I already see both hands. Okay, great. So for the people who raised 2 hands, does somebody want to tell me what they think this is? A cat? A cat? Did I hear? A lion. Great. Okay. So it's starting to crystallize. This will become even more apparent as the video plays out. We can tell that this is a lion, despite the fact that I've left out quite a bit of structure that characterizes our visual world. So I've left out color, I've left out grayscale, I've left out average pair correlations, which are characteristic of natural visual scenes. And yet the patterns that are left over still contain a significant amount of information that we can use to make sense of what we're seeing, to make sense of the outline of the lion, the texture of its fur, the structure of the grass in the background. Okay, so this approach of dialing structure into randomness has been used for a long time in the field of visual psychophysics to probe our own visual sensitivity. And so this is done much more rigorously in the lab than what I've shown you here. One example of this, this is work from Jonathan Victor and Mary Conti, where they isolate certain visual patterns and they place them on an otherwise noisy background. And they ask human observers, like all of us, to identify the location of this non-random pattern. And so perhaps you can see here that there's a strip of correlated texture near the top of this image. And so they ask human observers to identify the locations of these textured patterns and use this as a way to probe visual sensitivity. And so the way that they would do this in practice is to bring one of us into the lab, sit us in front of a computer screen, and present us with this type of image. And they'd ask us to tell us where this textured pattern is, and they'd give us 4 choices. They'd tell us it could either be in the top, bottom, left, or right of this frame. But the trick is, they don't let you stare at this image for a long time. They actually present it very quickly, so you don't have time to scan across the image. So in practice, what they do is they ask you to first fixate on a cross in the center of the screen, and then they quickly flash this stimulus and replace it by a noisy mask. Okay, so if I were to unfold these frames in time, again, they ask people to fixate on a cross, then briefly flash the stimulus and replace it by noise. And for the stimulus in this center frame, they ask people, where was this strip of texture? Top, bottom, left, or right? So, of course, I think the easiest way for you to get a feel for this is to do a couple examples yourself. So I'm going to give you this task as best I can in this setting. So I'm going to have you fixate on a cross in the center of the screen. I'll quickly flash the stimulus and I'll replace it by noise. And then I'll ask you to tell me where the correlated strip of texture is, and I promise you it'll be either in the top, bottom, left, or right of this image. Okay, does everyone understand? Great. This is somewhat limited by my own speed in making this work, so we'll see if we can do this. Okay, is everyone ready? All right. How many people saw something in the top, in the bottom, in the left, in the right? How many people saw nothing at all? Nice. Okay, great. So this is what you were shown. It was a strip of texture in the bottom of this frame. We'll do one more example. Are you ready? Okay. Top, bottom, left. Nice. Right. Yes. You guys are awesome. Okay, great. So this is what you were shown. If we put these side by side, we can see from looking at these, we could also see from your performance that the second example was much easier than the first. And it's much easier for us to see the texture in this second example than the first example. Now, it turns out that your performance in this very quick example is consistent with what Jonathan and Mary measure in the lab. So if they take human observers and show them patterns like the first example that I gave you or like the second example, people tend to be much more sensitive to these patterns here, like the second example that I showed you, than the first example. And if we had more time, I could show you more textures that are intermediate between these and for which you would have intermediate sensitivity. Okay. Now, even though you were much better at the second example that I showed you than the first, mathematically speaking, both of the patterns that I showed you had the same amount of structure in them. So what do I mean by that? Well, these patterns were generated by controlling local correlations between nearby pixels in an image. So to generate patterns like the first example that I showed you, you can control local correlations between 3 nearby pixels arranged in this L shape. And this is something that you can dial. So you can dial in or dial out these correlations and generate whole classes or families of different textures that interpolate between things that are purely random and textures that are highly correlated. And so you can use this as a knob and ask, how high do I have to crank up the structure in these different types of textures before people can reliably distinguish this from noise? And this is exactly how Jonathan and Mary measure visual sensitivity, and this is how we would measure your sensitivity in this type of experiment. Now, we can use these same types of approaches, these same types of methods to measure the statistical structure of the visual world around us. And it might not be surprising to you that our visual world is made up of a combination of these different types of patterns. But it turns out that some of these patterns, if we look over an ensemble of visual scenes, some of these patterns are much more variable and thus much more informative than other patterns. So to give you a sense of what I mean by that, if you imagine taking this 3-pixel window here and using it as a window to look through the world. So you look through this window, and everywhere you look, you see exactly the same thing. There's no variability in the measurements that you make. Then any particular measurement doesn't tell you anything about what it is that you're seeing. But if you look through this window, and everywhere you look, you see something slightly different, there's high variability in the measurements you make, then any particular measurement has the potential to tell you something about what it is that you're seeing. And so in this way, we would say that the patterns that show more variability are more informative. And so if we go out and we measure this variability across an ensemble of natural scenes, we see that it predicts which patterns you see well and which patterns you see poorly. So this means that even without having done this experiment, this example at the beginning of the lecture, and without having known the results of the psychophysics, I could have predicted that you would have been much better at the second example that I showed you than the first example, And I could have made that prediction based purely on the statistics of the visual world around us. Okay? So this is pretty cool. I think this is pretty powerful. We're going to dive into this a bit more and really understand what this means. But the claim that I just made to you is that you should be more sensitive to visual features that are more variable because they are more informative. Okay, so we're going to unpack this a bit over the course of the next 20, 30 minutes or so and understand more rigorously how this claim comes about. But for now, just bear with me on this. We can take this same claim and look at it in a slightly different way. So we can look at this as saying that you should be a particular way. You should be more sensitive to visual features that are variable. And whenever we start to say that you should be one way or you should be another, we're implying something about there being a performance advantage to being that way. There's some reason why it might be advantageous to be sensitive to these sorts of features. And here, we're arguing that that's because of some statistical properties of the visual world in which we live. And so this is related to the lawfulness of the world in which we have to operate. So this gets at the essence of the normative approach. It's precisely because the world is lawful that we can start to specify some strategies as being better or worse than other strategies, and therefore biological systems should take on some strategies as opposed to others. Okay. So the world around us is lawful. We know this. This means that animals and brains can exploit this lawfulness in order to achieve this performance advantage. And there are many different ways that a system could do this, and so we're going to be trying to talk about different ways that systems could achieve different types of performance advantages. But some of the ways that we're going to try to tackle today are thinking about how a system might remove redundancies that are present in the world around us in order to build efficient and compact representations of information, how systems might combat noise in order to correct errors, how they might resolve ambiguities in order to reduce uncertainty about unobserved states of the world, and how they might make predictions in order to improve performance not just now, but into the future. Okay, so these are a bit abstract as stated, but we're going to try to unpack each of these throughout the course of the lecture and understand how exactly systems could improve performance along these different types of dimensions. Okay. So this is the essence of our normative approach, that the performance of a system can be related to the lawfulness of the world in which that system has to operate. And when we start to apply the normative approach, the way that we usually start is to start by specifying a few different quantities. So we start by specifying a function that we think a system needs to perform, and the context in which that function needs to be performed. And then we specify constraints on the system that will perform this function. And so these constraints can take on many different forms. These could be constraints on precision, accuracy, speed, time, energy. And then given this function, the context, and these constraints, we ask what would be the best solution, the best strategy for achieving this function subject to these constraints. So in the example that I just gave you, the function that we specified that the visual system needs to perform is maximizing information about different types of visual patterns. And the context in which we think the visual system has to maximize this information is over the ensemble of natural visual scenes, so the natural visual world in which we live. And we think the visual system has some constraints on how well it can do this, and these have to do with bandwidth and noise constraints. And we'll get into the nature of these constraints as we go forward. But given this problem setup, we then derived the optimal solution for maximizing information subject to these constraints and found that what the visual system should do is be tuned to patterns that are variable. And so by the end of this first chunk of the lecture, I hope to sort of give you a better understanding of how we actually go about formulating this problem and under what specific assumptions this result is the case. Okay. So the example that I've given you so far is thinking about how we sense different properties in the world. Ultimately, we'd like to think about how those impact the actions that we might take, how these impact behavior. And these actions, of course, in turn impact how we exchange information with the world. And so what I've been arguing to you so far is that if there is structure in the world around us, if there is this lawfulness, then there is structure to be exploited in the way that we sense and in the way that we act. And given that biological systems have constraints on how they can sense and how they can act, then we take these constraints explicitly into consideration. And because of these constraints, we think that systems like the brain use internal computations to link sensation and action. These would be computations like inference and like prediction. And so we'll be talking today about how these different computations inform one another. And of course, it's not just a feed-forward process like I've drawn here, but each of these computations can both inform and constrain each of the other. So we're going to be trying to understand these different relationships. And so I'm going to sort of break the rest of the lecture into a few different parts. We're going to start by thinking about this, diving into this sensory processing side of things, and think about how sensory systems can remove redundancies that are in the world and combat noise. Then we're going to, in part two, think about how this sensory information can be used to guide inferences, so to infer things that are unobserved about the world. And then in part three, we're going to think about how these inferences can be used to form predictions about what is to come in the future, and how these predictions can be used to guide actions. Okay, so this is sort of the outlook for the rest of the afternoon. But we'll start with part one, thinking about removing redundancies and combating noise in the world around us. Now, these ideas are not new. People have been thinking about removing redundancies and combating noise for a long time. We already heard from Barlow, who is one of the proponents of this, but even earlier was work from Fred Atniav. And this is a quote from Atniav in his 1954 paper. And here he says, "When we begin to consider perception as an information handling process, it quickly becomes clear that much of the information received by any organism is redundant. This means that if we know at a given moment the states of a limited number of receptors, we can make better than chance inferences with respect to the states of these and other receptors. And this is precisely equivalent to an assertion that the world as we know it is lawful." Atniav went on to say, "It appears likely that a major function of the perceptual machinery is to strip away some of this redundancy in order to describe or encode incoming stimulation in a form more economical than that in which it impinges on the receptors." All right, so already Atniav was talking about this relationship between the lawfulness of the world and the properties of sensory and perceptual systems that could exploit this lawfulness in order to, in this case, remove redundancies. So Atniav, along with Barlow, laid the foundations for the framework of efficient coding that we're going to be talking about. Barlow went on to formulate some of these same ideas in the context of a channel coding problem. And so this he framed under what he called his redundancy reduction hypothesis. And here he was thinking about how information could be communicated across a noisy channel. And so here is a schematic of this channel down below. Barlow was thinking about a set of input messages that would need to be communicated along this channel. And so we could think about these as sensory stimuli. These input messages would then be recoded, or as we might think of encoded, to produce a set of output messages, or we might think of these as neural responses. And so as soon as we start writing it like this, we can think about this encoding step as a mapping from a stimulus onto a neural response. And we'll be talking about this mapping probabilistically. So we can specify the probability of measuring a particular response given a particular stimulus. And you'll see that I've already started to color code things here. This is because I'm going to start unpacking different elements of this, this channel coding problem, so I'm going to try to be consistent with these colors. Okay, so Barlow is hypothesizing that the goal of sensory systems was to communicate as much information as possible along this noisy channel, but subject to constraints imposed by noise and imposed by a channel with limited capacity. So he was thinking about squeezing these signals through some channel with some limited capacity C. And he hypothesized that the goal of early sensory systems was to communicate as much information as possible through this channel. And so we can write this in terms of maximizing the mutual information between the neural response and the incoming stimulus. And we can write this mutual information as the sum of two terms. We can write this as the entropy of the neural responses minus the conditional entropy of the responses given the stimulus. And in a minute, I'm going to sort of unpack exactly what we mean by entropy, but just bear with me for a moment. So this second term here, the conditional entropy of the response given the stimulus, tells us how much variability is there in the response if we exactly know the input stimulus. And so this tells us something about the noise in the response. So in the limit that there's very low noise in these input messages and how they're encoded, we can treat this, we can take this to 0. And in that limit, maximizing information is equivalent to maximizing the entropy of the response. Or as Barlow originally formulated it, he formulated his problem in terms of minimizing what he called the redundancy, and he defined redundancy as 1 minus the entropy of the response scaled by the channel capacity. And so the basic idea here again is that you're trying to communicate information through a channel with some limited capacity C, and you want to transmit as much information as possible. You want to fill that channel capacity, but you can't exceed that. So we're going to try to understand exactly what this means, but first we need to understand something about entropy. So I'm going to back up a little bit, unpack entropy, and then we'll come back to this. Okay, entropy. So to unpack entropy, I want you to think of a sort of cartoonish example to start. So I want you to imagine two different machines that produce different sequences of letters, A, B, C, and D, in random order. Now, if we watch these two machines for a very long time, we could count the number of times that each machine produced each of these letters. And if we watched machine 1, we would see that it produced each of these letters a quarter of the time. So a quarter of the time it produced A, a quarter of the time B, a quarter of the time C and D. If we looked at machine 2, we would see that it produced A much more frequently than the other letters. So half of the time it spits out an A, a quarter of the time it spits out a B, and an eighth of the time it spits out either a C or a D. So we can, in looking at these machines, define entropy in terms of the average number of questions we have to ask to determine the output of these machines with certainty. Okay, so we're going to start querying these machines, and we're only going to ask yes or no questions, and we're going to see how many questions we have to ask on average to exactly know the output. And this is what we're going to use to define entropy. Okay. So first, we can write this average number of questions as a sum over the number of questions that we have to ask for each option, where we have 4 options here, A, B, C, or D, times the probability of each option. All right, so if we expand this out, here we have 4 options. That would mean the number of questions we have to ask to determine that the output is A times the probability of A, plus the number of questions for B times the probability of B, and so on. Now, it turns out that the most efficient way to ask questions of this machine is to ask them in a way that divides the answer space in half with every question. So I'll show you what I mean by that. So let's take machine 1. Machine 1 can produce A, B, C, or D. And so we want to ask a single yes-no question where we get the answer yes half of the time, and we get the answer no half of the time. Yes?
When you say determine the output with certainty, you mean literally the exact string?
No, the single output at a single time. So we're just going to be asking for, yes, exactly. So the question was, are we trying to produce the whole sequence, or are we just trying to, here we're just trying to determine a single letter in this sequence? Okay, good question. Okay, so we want to ask one yes or no question to divide the answer space in half. So one question that we could ask is the output either A or B, or is it not A or B? So if it is A or B, we know that it's one of A or B. If we get an answer no, we know it's one of C or D. And each of these things happens half of the time. So we can see that by looking at this histogram up here. Okay, so this is what we mean by dividing the answer space in half, and then we can repeat. So if we are on this branch here, so we know it's one of A or B, the next question that we could ask is it A? Half of the time we'll get a yes, and half of the time we'll get a no. But either way, we'll know if it was A or if it was B. We can do the same thing if we're on this branch here. So we can ask, is it C? We'll get yes half of the time, and no half of the time. And so you can see that no matter which of these outputs we're trying to identify, we have to ask a total of 2 questions for each of these. And you can see that based on how many arrows you have to traverse to get to this output. So this tells us how many questions we have to ask per option. And we know the probability of each of these options from this histogram at the top here. But you could also see that probability by multiplying what's along each of these arrows here. So if we multiply a half times a half, we get back a quarter, which is the probability that we would see A. Okay, so now we have everything we need to compute the entropy of machine 1. And if we do this for the first term in this sum, we know we have to ask 2 questions of option A, and option A has a probability of a quarter, and that this is the same for all of the other options that we might measure. And so we get that the entropy here is 2, and this is in units of bits. So now what I'd like you to do is to take a few minutes and work out the entropy of machine 2. And I'd like you to do it using the same setup that we've sketched out here. So I'd like you to figure out the right order of questions to ask in order to divide the answer space in half with each question, and then use that to compute the entropy of machine 2. I'll give you a couple minutes, and then we'll regroup. Okay, does anybody yet have an answer that they'd like to share? I see a hand in the back. Yeah? Great, great. Okay, how many people got 1.75, worked through it? Awesome. Okay, for those of you who haven't finished working through it, I'd encourage you to finish, and I'm happy to go through and sketch out how to do this in the break, so just come find me if you'd like to do that. Okay, so we saw that machine 1 had an entropy of 2 bits. If you work out the entropy for machine 2, you should get 1.75 bits. Okay, so you see that machine 2 has lower entropy than machine 1. And it turns out that in this case, when we have 4 options, the maximum entropy solution will give us 2 bits of entropy. This is the most that we can get. And this happens when we've evenly divided our probability among these 4 options here. Okay, another way to think about this is we're maximally uncertain about which option the machine will produce. Now, it turns out, and you can look at your notes to verify this, that the number of questions that we have to ask to determine each of these options is equal to negative log base 2 of the probability of that option. So if we take option A and we take the negative log base 2 of a quarter, we get back 2, which is the number of questions we have to ask to determine that the output was A. Okay, so you can check in your own notes that this is the case. But this means that we can now write entropy as the average over this number of questions. And so we can write the entropy as negative p log p summed over the options that we have. So this then gives us our formal definition of entropy. Okay, so we can think of entropy as giving us the average number of yes-no questions that we have to ask to determine the output of this machine with certainty. The higher the entropy, the more uncertainty we have about what this machine will produce. And another way to think about this is that that we have a greater reduction in this uncertainty when we make a measurement. So the more uncertain we are, the more we can reduce our uncertainty by making a measurement. And so you can see how this relates back to gaining information. We gain information by reducing this uncertainty. Okay, so now we're ready to come back and revisit some of the ideas that we were visiting with Barlow. So coming back to Barlow's redundancy reduction hypothesis, again, the idea was that sensory systems would maximize information about their inputs, and in the limit of low input noise, this is equivalent to maximizing entropy, and we've just seen how you could go about maximizing entropy in terms of distributing your probability equally across your different response states. This is often called the classic efficient coding hypothesis, and by classic I mean that we're specifically working in this low noise regime. Later we'll talk about how the ideas in this would change if we're dealing with high input noise, but for the time being I want us to work in this low input noise regime. And we've just seen how we could think about the entropy of a machine that produces different sequences of letters here. And so now I'd like to think about this machine as a tuning curve that is communicating information about some incoming stimulus. And so if we know that we want to maximize entropy at the output, and we know something about the distribution of stimuli at the input, then we can work backwards to think about what this tuning curve should look like in order to guarantee that. So that's what we're going to try and be doing. Okay, so let's imagine that we have a stimulus distribution that looks like this. So this is a PDF of a particular type of stimulus. And we'd like to design a tuning curve that maps this stimulus onto here 2 different responses, A or B. So we have 2 different response levels, and we'd like to maximize the entropy of our responses, which means that we want to use each of these responses with equal frequency on average. So we can work backwards, knowing this, to figure out how we should design this tuning curve in order to guarantee that we use these responses with equal frequency. And one way that we can do that is by using them to partition this stimulus distribution, to essentially cut it in half. So if we cut this distribution in half, we can then assign half of this distribution, we can give it a response A, and assign the other half of this distribution to response B. And this tuning curve will guarantee that we use each of these responses equally frequently on average. Okay, so this you could think of as a binary tuning curve. A neuron doesn't fire or it does fire. Now we can see what this might look like if we have 4 response levels instead. So here we have A, B, C, or D. And in this case, we know we want to evenly distribute our probability across these 4 levels, so we want to use them each a quarter of the time. And this means that we can work backwards to divide our stimulus distribution up into 4 equal probability chunks. So now each of these chunks here has an equal probability density. then we can assign each of these chunks to a different response level. So we can assign the left chunk to A, another chunk to B, another chunk to C, and the rightmost chunk to D. And in this way, we can build up a tuning curve that will again ensure that our responses are used with equal frequency at the output. All right? So this idea of working backwards to derive a tuning curve that would guarantee that you get maximum entropy of your responses on the output, this was used in one of the first empirical tests of the efficient coding hypothesis. This is work done by Simon Laughlin back in the 1980s. So Laughlin was studying the response properties of neurons in the early visual system of the blowfly, large monopolar cells. And these neurons are sensitive to changes in light intensity, but they have a finite dynamic range. And so Laughlin was interested in understanding how these neurons should most efficiently use their limited dynamic range in order to maximize information about their inputs. And again, he assumed that we were working in this low input noise regime where maximizing information is equivalent to maximizing entropy. And so he went out and he measured the distribution of light intensity found in the world. So he measured this empirically. And then he asked, given this distribution of inputs, how should my neuron with finite dynamic range allocate this dynamic range to this input distribution? And so the way he formulated this problem is to think of this neuron as having a finite number of what he called response states. And so he wanted to ask how these response states should be allocated to this distribution. And so he derived the tuning curve that would guarantee that each of these response states would be used with equal frequency. And that tuning curve looks like this. And we can understand that tuning curve using the same sort of lens that we've just been working out. And we can do that by looking at this tuning curve through the lens of these response states here. So if I color each of these response states a different color, and I project them back onto the tuning curve, and then I project these points back up to this stimulus distribution, you can see that this tuning curve essentially partitions this distribution into equal probability chunks, just like we worked out before. And so you can think of this tuning curve as assigning different chunks of this distribution to each of these discrete response states. And this again guarantees that this histogram of response states is flat at the output. Probability is distributed equally among them. And so this is often referred to as histogram equalization because we're equalizing the histogram at the output. So Laughlin used these ideas to derive the optimal tuning curve here for maximizing entropy about this particular input distribution that he measured in the natural world. And then he compared this to the responses of these blowfly neurons. And he found a pretty nice match. Right? So this was one of the first empirical tests of the efficient coding hypothesis. So since that time, people have gone on to use these ideas to understand a range of different tuning properties, which we'll get into in a moment. But I want to just step back and remind you that everything that we've sort of worked out so far has been assuming, again, that we have this constraint at the output, and we've been implementing this constraint in a very particular way. So we've been assuming that we have a constraint on the number of discrete responses that this neuron could produce. And so if we maximize entropy subject to this particular constraint, we find that the maximum entropy distribution looks flat, like we see here. But this isn't the only constraint that we might care about. And so, for example, if we add a constraint on the mean firing rate in addition to the number of responses, does anyone know what this distribution would look like? So if we maximize entropy subject to a constraint on the mean firing rate, we get an exponential distribution. If we add on another constraint, not only on the mean, but on the variance in firing rates, we get a Gaussian distribution. And in these two cases here, this is not specific to having a constraint on the number of responses, so we could also take this to the continuum limit and implement these same constraints. And these are things that you can work out analytically, so you can formalize this using Lagrange multipliers, maximizing entropy subject to these constraints. So if you're interested to see how these come about, come talk to me in the break, or we can work this out afterwards, and you can see how these particular distributions come about. Okay. So the constraints matter in terms of the form of the distribution that we get, and you can see here perhaps why we might see these types of distributions coming about very frequently in biology and neuroscience. So these are the solution to the maximum entropy problem, subject to these particular constraints on mean and variance in firing rates. Okay, so up until now, we've been thinking about how to design a single tuning curve. But as I mentioned, people have been using these ideas to think about designing other sorts of response properties. Things like a linear filter, for example, so something like a receptive field. So if we start to formulate this same problem in the context of a linear filter, then we might want to think about a stimulus that, say, depends on 2 dimensions of space. This might be an image. And we can think about convolving that image with a linear filter like a receptive field to produce a response that depends on space. Okay, so this type of setup was worked out also by Laughlin only a year or so later and colleagues, where they were interested in understanding how to design a linear filter to remove redundancies that were observed in different natural images. So here they were looking at correlations between 2 different points in space, and they were asking what would be the best linear filter to remove the redundancies that you see in these correlations. And so if you derive this optimal filter, you find that it looks like a center surround receptive field where there's local excitation in the center and some inhibition on the sides here. You can work this out not just in space, but also in time. So if you include temporal correlations, you can work out that the optimal filter should have this center surround receptive field, but it should be biphasic in time, so that you start with excitation in the center that transitions to inhibition over time. Now, these 2 results here deal with very low-level correlations between 2 points in an image, but people have generalized these results to higher-order correlations and have derived things like edge detectors or Gabor filters. So here are examples of spatial receptive fields, different snapshots of different spatial receptive fields on the top, and how those receptive fields should evolve in time if you include these temporal correlations. So these ideas have been used to understand the emergence of different receptive field properties that we see in different stages of the visual system. And so all of this we can understand from the perspective of a linear filter that here has been derived in space and time. But I think it's actually easier to think about some of these ideas if we work not in the space-time domain, but in the frequency domain. And we can see how some of these ideas tie back to what we worked out earlier. So if we take this equation and we transform it into the frequency domain, what was a convolution in space and time becomes a multiplication in the frequency domain, and this is a bit easier to work with. So now we can think about the power of a linear filter as it relates to the power of our input distribution, and we can think about how we would design this filter in order to flatten that power spectrum at the output. So here, if we look at the power spectrum as a function of spatial frequency, the analog to what we worked out earlier would be that we want to flatten this spectrum at the output. Okay, this is analogous to the histogram equalization that we described earlier. And so if this is what we have at the output, then we can ask what is the filter that we should use depending on what we have at the input. So people have measured the power spectrum in natural scenes, and this has a characteristic 1/f² fall off that you might be familiar with. This has been measured many times. So here's an example from David Field. Here he's looking at the amplitude spectrum for 6 different natural images, and you can see that the amplitude falls off as 1/f, which means the power spectrum falls off as 1/f². Okay, so now we know that we have this 1/f² power spectrum at the input. We want to get this flattened spectrum at the output, and so we can ask what should be the power spectrum of our filter that guarantees this. So can you guys give me some indication? Yes? I'm sorry, I didn't catch you. So you would want, if I understood you correctly, you would want a filter that goes like f squared. So when you multiply it by 1 over f squared, you get something flat at the output. Great, thank you. So that's exactly right? So if we multiply a filter that goes like f squared times a spectrum that goes like 1 over f squared, we get something that's flat at the output. All right, and this frequency dependence has been measured, for example, in neurons in the LGN of the cat. People have shown that this guarantees this flat output spectrum at the output of this transformation. Okay, so this is an example of what we would call a whitening filter, and it whitens the output, which means that it creates this flat power spectrum. And this is what we would want, again, in the limit of low input noise. So everything we've worked out so far is in the limit of low input noise. It turns out that if we start to consider, so if we add noise in at the input, this no longer is the optimal solution. So in the limit of high input noise, the optimal filter looks more like a low pass filter, than a whitening filter. And in fact, you can derive a whole family of different solutions that interpolate between these, depending on how strong the input noise is relative to the output noise. And so this has been done analytically. So here you can see a derivation of this optimal tuning. Here are these white solid lines compared to human visual contrast sensitivity. And so you can see, as a function of increasing input noise, a transition that goes from something more like a whitening filter at low input noise to something that looks like this low pass filter at high input noise. So we see that we get a whole spectrum of different solutions depending on the relative strength of our input noise and our output noise. And here we've expressed this in the frequency domain as comparing the sensitivity of our filters to this input spatial frequency. But you might also see this comparison with respect to the power spectrum of natural images rather than the spatial frequency. So we can transform these results, knowing the relationship between frequency and power, to look at sensitivity now as a function of power. Right? This has also been derived here by Van Hatteren, and you can see that now as we move towards increasing input noise, we're moving sort of higher up in these curves. So the reason that I wanted to get to this point is because now you can see that in the limit of high input noise, sensitivity should be tuned in proportion to the power or the variability of the input signal. And this result is something that we derive in a particular limit of this efficient coding framework. And so we can now come back full circle to what we introduced at the beginning. So I told you that you should be more sensitive to patterns that are more variable in the world around us. And the way that we derived that solution was in this limit. So in the limit of high input noise, sensitivity should be tuned in proportion to this variability, and this allowed us to make this prediction of how your visual sensitivity should scale with the variability of statistical patterns in the visual world. All right, so this allowed us to make and test these predictions, but this was in a very particular regime of efficient coding. Okay, so now, great, okay. So we've seen how we could think about efficient sensory coding in terms of both removing redundancy and combating noise. And we've seen that there's actually a whole spectrum of different solutions that you can get by sort of interpolating between whether you have strong noise constraints at the output or strong noise constraints at the input. So when you have strong noise at the output, the optimal solution is to remove redundancies. When you have strong noise at the input, the optimal solution is to try to combat some of that noise. And so you'll see these different regimes of efficient coding referred to by many different names. So when people talk about removing redundancies, they'll talk about whitening, decorrelating, histogram equalizing. When people talk about combating noise, you'll hear this in terms of error correction and enhancing correlations. And in fact, we see that this whole family of different solutions sort of falls out of the same framework under different considerations of the constraints that are relevant to that system. Okay, so now we're going to transition. We're going to take a bit of a break, and then we're going to come back after the break and talk about how this efficient sensory coding can inform or constrain downstream computations like inference. So how we could use the output of these encoding schemes to infer unobserved properties of the world. So with that, I'm going to have us break. If there are any questions, I'm happy to answer them now. But we're going to come back at 1:20, all right? So come up and ask me questions if you have them. Otherwise, take a bit of a break, and then we'll regroup in a little bit. Oh. Yes.
Might be better if I put it
Yeah. Yeah, absolutely. What, come on up. everyone. We're going to go ahead and get started again. So if you take your seats. Okay. So in the first part of the lecture, we focused on how sensory systems could efficiently encode information about the outside world. And now we want to think about how they could use this information to guide inferences, to infer unobserved properties of the world, and in doing so, resolve ambiguities. Okay, so up until this point in time, we've really been thinking about this problem. So how we might design a smart encoding for encoding incoming stimulus features into some neural response, like a firing rate. But something that was implicit in everything that we worked out in the first part of the lecture is we assumed that this distribution of stimulus features was stationary. But in reality, animals encounter distributions that are changing in time, that characterize different environments that they might be in. So as a very simple example, if we are trying to detect a tiger, we might process a scene very differently if that tiger is in the field than if that same tiger is in sort of a forest setting. Right, and we can see this, we can make this a bit more explicit if we actually select patches from each of these different scenes. And if we were to look at these local textural features in these patches, much like the textural features we were looking at earlier, we would see that these local statistics look very different from one scene to another. And so it might be to our advantage to process these two different scenes differently. Now we can make this again more concrete and quantify this. So we can do this by picking out a particular feature that we might care about, something like one of these oriented edges, and we can filter those features out of these image patches. And if we were to do that, we would see that the distribution of image features that we measure in the field is different than the distribution of features that we would measure in say, the forest. And so using the identical arguments that we laid out in the first part of the lecture, we would argue that sensory systems should be tuned differently if they're facing one of these distributions than if they're facing the other. And so we can think of these as two different contexts that a sensory system might encounter, each of which is signaled by a different distribution of stimulus features. And so if we're wanting to design efficient encoding strategies, then we would want to be tuned differently in these two different settings. And so we would expect, based on the same arguments that we laid out earlier, that we would want to tune our tuning curves differently if we're in the field versus in the forest. Now, the sort of basic flaw in the argument that I laid out for you here is that this assumes that our sensory system knows which context it's in and can flexibly or immediately toggle between these two different tuning curves. But in reality, sensory systems have to make inferences about this underlying context from this same distribution of incoming stimulus features. So sensory systems have to use these same stimulus features to infer whether I'm in the forest or whether I'm in the field, and use that information to then adjust these sorts of tuning curves. So we can think about this process by adding on here another step, which is using the output of this sensory encoding to make inferences about this underlying context. And so we're going to build up an optimal Bayesian observer model that tries to infer this underlying context, and it's going to do that by computing the relative probability that it's in the field or the forest, or whether it's in turquoise or purple. Okay, as soon as we introduce this inference step here, we can no longer think about the forest and the field as two entirely separate entities that we optimize separately, as I've sketched out here. We really want to think about how a system could make inferences about this in time. So if the environment is changing in time between these two contexts, then we want to think about how a sensory system could infer changes in context. So we're going to consider a very simple setting in which the context can change between the forest and the field, or between green and turquoise. And we're going to simplify this distribution of stimulus features here and assume that in one context, the distribution of features is Gaussian with a low mean, and in the other context, the distribution of stimulus features is Gaussian with a high mean. And then we're going to encode these stimulus features like we sketched out in the first part of the lecture, and then use the output of this encoding to build and update this Bayesian observer model. And so once the Bayesian observer has builds and updates this estimate of which context the environment is in, it can in principle use that estimate and feed it back upstream in order to adapt this encoding step. All right, so this is one way that sensory encoding and inference might work together or constrain one another. And so we're going to walk through and derive this optimal Bayesian observer model in this fairly simple setting here. And to do that, I need to be more specific about exactly what we're specifying here. So I'm going to introduce a little notation, and I'm going to formalize this a bit, and then we'll try to derive this Bayesian observer model. Okay. So I'm going to refer to my context by theta, and because it's changing in time, I'm going to give it a time index t. And this context is going to generate different distributions of stimulus features, and I'm going to refer to these as low and high. Low because in one case this distribution has a low mean, and high because in the other case it has a high mean. So you can see that the context here is switching between low and high over time. And ultimately our Bayesian observer is going to be inferring whether the environment is in the low state or the high state. Now I'm going to specify specific dynamics for these changes in context, and here I'm going to assume that the context at time t only depends on the context at time t minus 1. This is a Markov assumption about the dynamics of the environment. Now, in this case, when the environment only has two states, then this probability distribution is specified by a 2x2 matrix that tells us the probability of transitioning from low to high or from high to low from one time point to the next, or from staying in the same context. So here I'm going to specify that there's a probability PS for P switch for switching between these two different contexts. So that means that the probability of switching from low to high or from high to low is given by this P switch. And the probability of staying within the same context, whether it's high or whether it's low, is 1 minus P switch. Okay, so this specifies the dynamics of our environment, of our context. Now, I'm going to assume that at any point in time, the value of the context specifies the distribution of sensory stimuli. And so the stimulus at time t, which I'll call ST, is determined by the context at time t and nothing else. And we're going to take this distribution to be Gaussian with a mean centered at theta t. So this just represents what we sketched out above. Okay? So these are the assumptions that we're making about our simple environment, and now we're going to derive a Bayesian observer that can infer this underlying context. We have to start by specifying exactly what the Bayesian observer knows. So we're going to assume that the Bayesian observer knows both of these distributions. It knows that the environment is in two states. It knows how likely it is to switch from one state to the other, and it knows that given the context at a particular time, it knows the distribution of incoming stimuli will be Gaussian. So what doesn't it know? It doesn't know the specific value of the context at a particular time. Right, so we want to estimate the probability that the context is theta t given the history of past stimuli. And I've written this in a very particular way. So I've broken apart the stimulus that occurs at time t from the history of stimuli that occurred before time t. And we'll see why I wrote it this way in a minute. So we're going to work through how to derive this quantity, what we want, from what we know. And the derivation that I'll be working through follows the derivation that was laid out in this paper by DeWeese and Zader. So if you're interested in digging back through the math, I would point you here. Okay, so we want to estimate this probability distribution from what we know, and we're going to build up this estimate using Bayes' rule, using the laws of probability. So just to sort of refresh on this, if we have a joint distribution of two variables, a and b, we know that that's equal to the joint distribution of b and a. And we can expand each of these distributions. So we can write p of a and b as p of a given b times p of b. And we can similarly write everything on the right-hand side as P of B given A times P of A. Now, if we divide both sides through by the probability of B, then we get this expression for P of A given B. And this is Bayes' rule. This just follows from the laws of probability. This is for 2 variables. If we have 3 variables, we can generalize this expression. So now if we have probability of A given B and C, we can write this in terms of probability distributions over those same 3 variables. So now, given that I've written it like this, we can substitute back in things that we care about. So if we let A equal theta of t, B equal S of t, and C equal S of tau less than t, then we can write down an expression for what we want. This is the quantity that we want to estimate in terms of other distributions. And what we'll be doing over the next few slides is simplifying this expression so that we can get what we want in terms of things that we already know. Okay? Okay. So the first thing that I'm going to do is start by simplifying this distribution up here. So we said earlier that the distribution of stimuli at time t depends only on the context at time t, and it doesn't depend on the history of past stimuli. So we can remove this dependence and simplify this. Now I'm going to add one more step, and I'm going to ensure that this distribution is normalized here. And so that when I sum over theta t, I want to enforce that this distribution sums to 1. Okay, so if we sum everything on the left-hand side here and set it equal to 1, that's equivalent to summing everything on the right-hand side. And so we can write this sum as follows. So here you can see that this term in the denominator here doesn't depend on theta t, and so we can pull it out of the sum and multiply it by this 1 on the left-hand side. And so we get an expression for this distribution in the denominator here in terms of a sum over everything in the numerator. And so I'm going to define this to be a normalization constant, and I'm going to call this omega. And this is a constant that will be changing over time, but this is a constant that we can work out if we know these distributions here. Okay, so this is our normalization constant. Now we have the probability of stimuli given theta t. This is our stimulus distribution that we know. And now we're going to simplify this distribution here on the right. So I'm just going to write this down below, and I'm going to set it equal to itself. And then I'm going to expand this out by summing over the value of theta at time t minus 1. Okay, so we can expand that quantity in this way. Summing over theta of t minus 1, and now we can simplify this. So again, we know that the context at time t depends only on the context at time t minus 1, not on the history of past stimuli. So again, we can remove this dependence. And now if we focus on this second term here, I can rewrite this by separating out the stimulus at time t minus 1 from the history of past stimuli that preceded that. And if I change the color scheme here, you'll see that this quantity looks exactly like this quantity, but just shifted 1 time step in the past. Okay, so what we're going to be doing is writing down a recursive relationship between this distribution that we want in terms of that same distribution at 1 time step before. All right, so this might look a little bit longer, but we've actually simplified things, and now we can write down what we have in terms of things that we know. So I'm going to give each of these terms a number, and then I'm going to sort of map this back out, map this onto the problem that we started with. So just to remind you, this is the problem that we started with. We have this changing context, and this context specifies 2 different distributions of sensory stimuli. So when we have only these 2 different contexts, this distribution here, the probability of theta t, can be expressed as a single number at any point in time. And that's the probability that the environment is in the low context at time t. And so I'm going to write this in the following way. I'm going to write that as piece of t superscript L, the probability at time t that the environment is in the low context, and it's defined exactly as above, assuming that we're only in the low context. Once we know this distribution, then we know the probability of being in the high context is 1 minus this. Okay, so once we've worked things out for the low context, we can get back the probability of being in the high context. Okay, this second distribution here, this is our distribution of sensory stimuli. These are our Gaussian distributions that we sketched out here. But here now we want the distribution of stimuli given that we're in the low context. Okay, so that's this expression here. Now moving on to this third term. This is that 2 by 2 matrix that we worked out earlier. The transition probability of switching from high to low or low to high or staying within the same context. And again, we want to focus on this top row of the matrix when theta t is equal to theta L. And now if we multiply this by this fourth term, this again is the same distribution as the one we're looking for, but one time step in the past. Right? So if the environment is in the low state, that's the probability of being in the low state at time t minus 1. If the environment is in the high state, that's 1 minus this probability. And so what we're going to do is take this top row of this matrix and multiply it by this column vector to get the product of these two terms. And so that expression looks like this. Okay, so we've just taken this row times this column, and this is what we get back. Okay, so now we've written an expression for what we want in terms of things that we know, and now we can try to understand exactly what this expression means. So what we've derived on the left-hand side here is what we would call the posterior probability of being in the low context at time t. And we wrote this as a function of what we would call the prior probability of being in the low context at time t minus 1. So how probable were we at the last time step that we were in the low context? And then we would multiply that times the probability that the context stayed low from the last time point to this time point. And we would add that to the prior probability of being in the high context times the probability that the context changed from low to high. Together, we multiply this by the likelihood that the stimulus that we observe at time t was generated in the low context, and together, this gives us back our posterior probability. Okay, so in this way, we've defined an expression for the probability of being in the low state at time t in terms of things we know about the stimulus distribution and the dynamics of the environment and how they switch between contexts. So written as it is, this captures sort of the key aspects of Bayesian inference. The posterior tells us how probable our hypotheses are about the state of the world. And here we're evaluating two different hypotheses, that the environment is in the low context or the high context. And we define this posterior, or can build up this posterior in terms of the likelihood, which tells us how probable are our sensory measurements given these hypotheses about the state of the world, and how much did we expect these hypotheses based on our previous experience. Now, many of you will recognize this from the tutorial that you may have come to last year, Weiji's tutorial on Bayesian inference. So the basic idea here is that we can take our prior, how much we expect our hypotheses based on our experiences, combine it with this likelihood, how probable are our sensory measurements given these hypotheses, and use this to evaluate how probable these hypotheses are. And then if this is evolving in time, we can use this posterior to inform our prior at the next time step. And we can do this recursively. Okay? So for those of you who haven't checked out Weiji's tutorial, I'd encourage you to do that. It's online. He went into much more detail in terms of how you can use Bayesian inference to understand aspects of your own perception. For example, how you might perceive different types of two-dimensional images based on the types of three-dimensional structures that might have generated those 2D images, how we can understand different types of illusions that we might experience. So I'd encourage you to go back and check that out. But for now, I want to sort of move forward and think about how we can couple this process of Bayesian inference with what we've already been talking about, this efficient sensory coding. So up until now, we've been thinking about how you could efficiently encode different stimulus features using different forms of this encoding. And we started out by talking about encoding in terms of prioritizing features in order to maximize information. And now we've added on this additional piece of wanting to use the output of this encoding to perform inferences, to infer something about unobservable states of the world. And here we built up a posterior distribution for evaluating our hypotheses about those states of the world. And so in doing this, we can actually rethink what we mean or what we might want from this encoding step. So rather than thinking about this encoding purely in terms of maximizing information, we could think about this encoding in terms of prioritizing features that are useful for testing and evaluating these hypotheses about the states of the world. And if we think about encoding in this way, then we can prioritize features that are useful for building accurate posterior distributions about the states of the world. And given this type of model, we can make predictions about how the environment might change, time steps in the future, and we can use this to dynamically adapt how we encode information. And so in this way, we can start to couple this process of encoding what's informative about the world and using this to build up models of underlying states of the world. Okay? Is there a question? Okay. So up until now, we've talked about how you could design efficient sensory encodings to remove redundancies and combat noise. And we've seen how you could couple this with inference in order to resolve ambiguities about the sources of those stimulus features, and how you could make short-term predictions about how the environment might change from one time step to the next, and use this to change how you might prioritize different sensory features. But now I'd like us to move and think about how we might build longer-term predictions and use those predictions to ultimately guide actions. So we want to think about how these predictions can be translated into selecting and guiding actions. These actions will inform all of these earlier stages, and they'll also inform and influence how an animal or an agent interacts with the outside world. So we're now starting to build in more of these sort of bigger feedback loops. Okay. Now, there have been many ways of thinking about how actions can influence the state of the world and how an animal or an agent should choose actions in a smart way. So one class of these types of approaches focuses on gathering information. These would be approaches like infotaxis. Another class of these approaches deals with maximizing reward. And these would be approaches that come from the field of machine learning. And so these are different ways of specifying how an animal or an agent should choose different types of actions in order to get different things from the world. In one case, extract information. In another case, collect and maximize rewards. I'm going to focus on this second branch here, and I'm going to work from Sutton and Bartow's 2018 book. So if you want to sort of dig into some of the derivations, that's where I'd point you. If you're interested in hearing more about these sort of information-seeking types of approaches, come and talk to me offline. Okay, so if we're moving into the world of machine learning, we're really reinforcement learning, excuse me. We're focusing on the interaction between this agent, everything in this purple box, and the outside world. So we're going to assume that the world is signaled to the agent in terms of different states. So we describe the world by a certain state S, and that's signaled to the agent. And that agent can use this state of the world to guide its actions. Now, in what we were talking about earlier, we were talking about having to infer something like this state. Now I'm just going to assume that this is known, that the agent has this information. But in practice, we might want to think about how the agent would actually infer this underlying state from incoming sensory measurements. Okay, but let's say the agent has access to this state. It can now use this state to guide actions, and it can do that through a function that we refer to as a policy. And so a policy specifies how probable it is to take a particular action given that you're in a particular state. Okay, so this policy can be used to select a particular action A, and that action will affect the state of the world. And it affects the state of the world through a set of dynamics that we can specify. And we often assume that these are Markov dynamics, but we can specify the dynamics of the world, and those are specified in terms of how likely it is if the agent takes action A from state S for the environment to transition to state S prime. This information is then signaled back to the agent at the next time step. So there's this continuous loop between the agent selecting actions, that changing the state of the world being signaled back to the agent. Okay, so everything that we've specified so far, we haven't said anything about rewards. So even without specifying anything about rewards, we can talk about the dynamics of the world and the policies that agents might use to select their actions. But now we're going to introduce the idea that the world could contain different rewards and punishments, and that the agent could use that information to change the way that it behaves. And so if we now introduce rewards in the environment, we can do that formally using something like a reward function that specifies how much reward the agent will get if it takes action A from state S and transitions into state S prime. And so you can see that this reward function will depend on the dynamics of the environment and the actual action that the agent took. And this information can then be signaled back to the agent, and the agent can maintain an internal estimate of how good or bad different parts of the world are in terms of the rewards that it receives. And so we often refer to these estimates or build up these estimates in terms of what are called value functions. And so we can specify, we can assign a value to a particular state of the world or to an action that was taken in a particular state of the world. And so these value functions maintain internal estimates of long-term expected reward. So how good do I think this state is? Or how good do I think taking this action from this state is? And by good, we're thinking about this in terms of how much reward I expect to accumulate in the long term. And now if you have these internal estimates, you can use them to inform your policy. So now you can decide how you want to choose your actions depending on what you think is valuable in the world. Okay. So we can use these types of ideas to understand animal learning in a variety of different contexts. Here's an example that many of you might be familiar with. So I'm going to try to tether these ideas to spatial learning and spatial navigation. So this is an example of a Morris water maze experiment where mice or rats are placed in a large murky pool, and there's a platform that's submerged underneath this liquid. That platform is shown here in blue. It's invisible to the animal. And you can see in the top video here, this is an animal who's exploring this pool for the first time and doesn't know where this platform is. And on the bottom, you can see an animal the same animal has learned the location of that platform and can go straight to it. Right? So in these types of paradigms, animals can learn to associate different cues in the environment with the location of this platform, and they can use those cues to very quickly find that platform once they've learned this association. And we can use this framework of reinforcement learning to understand how animals go about learning this. Now, we know that mice can solve these sorts of tasks. It turns out that other animals like flies can also solve this task. So this is a fly analog of the Morris water maze experiment where flies are placed in a circular arena with a hot floor, and there's one cool spot somewhere on the floor, and the location of that cool spot is tethered to different visual cues on the walls of the arena. And so here in this sped up video, you can see here's the cool spot in this yellow dotted box. Flies initially might run right through the cool spot, but when they find it again, they tend to stay put. In a minute, you'll see this cool spot shift over here, and all the visual patterns on the wall will shift with it. And so if flies can learn to associate the location of this cool spot with those visual cues, they can, in principle, reduce the time it takes them to find that cool spot. And this is what most flies do. Almost all of them. We can use this framework of reinforcement learning to understand how animals would learn to associate different cues in their environment with good spots or bad spots. Here, this might be the location of a platform or the location of a cool spot, and how they can learn to modify their behavior based on this experience. Okay, so I'm going to use this to try to sort of work through some of the details of how we can formalize this in the framework of reinforcement learning. And so I'm going to work with, assume this sort of spatial navigation task. So I'm going to imagine that we're living in some two-dimensional box, and I'm going to discretize this box into a grid. So there are different spots on this grid that an animal can move through, and I'm going to refer to each spot on this grid as a different state of the environment. So here now I'm defining states of the environment as sort of 2D spatial locations in this grid. That means that at any state on this grid, I have different actions that I can take, and I can move from the spot that I'm in to one of the adjacent spots on the grid. So this is how I'm going to define my states and my actions. Now we can define a policy in terms of how an agent would select an action given a certain state. So if you're at a particular point on the grid, your policy could specify how likely it is for you to turn right, left, up, or down, depending on where you are. And this policy is tethered to the state of the environment S. So it depends on exactly where you are. Okay? Now, if we add rewards or punishments into this environment, so if there are certain locations on this grid that are better or worse than other locations, then our agent can learn about these locations and can build up an internal estimate about how good or bad different spots of the grid are. And so that's maintained in this function that we call the value function. So here might be an example of that value function where the agent has assigned a different value to different spots on this grid. And so this would be a value function defined with respect to different states of the environment. But as I mentioned before, we could also define value with respect to the action that an agent takes from a particular state. So what I'd like us to think about now is the relationship between these two different quantities, the relationship between the policy and the value. And as soon as we start introducing places in the environment that might be better or worse than other places, then we start to face what's called the explore-exploit trade-off. So exploiting would mean taking actions that we think are good based on our current estimate of the environment. So we maintain this value function. We think that this spot in the environment here is very good. And so we move to that spot. We exploit this knowledge. The downside of that is we could miss better options in our environment. We could miss the fact that this is actually a higher reward spot. This is a better spot. So an alternative would be to spend some of our time exploring by choosing actions that we don't expect to be as good, but might lead to higher long-term payoff. And so we can think about how animals or agents might navigate this explore-exploit trade-off. And this is often impacts how people think about designing these sorts of policies. So how agents will choose an action given where they are. So there are different ways of choosing policies that balance exploration and exploitation differently. So an example of a purely greedy policy would be one that chooses the action that maximizes the value function. So given my estimate of value, I'm going to pick the action that I think is best right now. So this is a purely exploitative strategy. You can deviate from this a little bit and incrementally introduce some exploration using something called an epsilon greedy strategy, where epsilon is a small number. And so you can, with probability 1 minus epsilon, choose this greedy action and exploit the knowledge that you have. And with probability epsilon, you can choose a purely random action, and in that sense, explore. So this is one way to dial in some amount of random exploration into an otherwise purely greedy policy. Another alternative that's frequently used is something called a softmax policy, where you weight different actions according to their expected value. And so here, you choose actions in proportion to or related to how valuable they are. And here you often introduce what's called an inverse temperature parameter that dials this amount of exploration or exploitation. So if this parameter goes to infinity, then you move towards a purely exploitative strategy where the action with the highest value is the one that you select. Okay, so that's purely exploiting. If, on the other hand, you dial beta down to 0, then all of the actions become equally likely, and this is a purely exploratory strategy. So this is one way that people use to sort of build a strategy that balances exploration and exploitation. Now, I should pause here and say that when we think about applying these sorts of ideas to study animal behavior, I've completely glossed over the fact that animals have certain actions that they can actually execute, and there are energetic costs to executing these actions. And so it's not as straightforward as specifying that an agent can take any action that maximizes a value function. So in practice, we need to think more carefully about how we constrain the action space based on what we know that animals can or can't do. And so I'm going to gloss over this completely for the rest of what we're going to talk about today, but I think this is an important consideration when we start to think about how to apply these types of algorithms to study animal behavior. But for now, I'm going to assume that we pick one of these strategies, like this softmax policy here, and I want to think about how an agent could use that policy to build up an estimate of value. Okay. So in all of this, the ultimate goal that we set out earlier is to maximize this expected long-term reward. This expected long-term reward is often referred to as the return. It's given the symbol G, and it's defined at a particular time t. And this is defined as the sum over rewards starting at time t plus 1 and looking all the way into the future. Okay, so if we want to maximize expected long-term reward, we want to collect as much reward from now into the future as possible. And if we write the return like this, then we're assuming that all rewards from now until whenever are equally important. We could alternatively preferentially care more about near-term rewards than about far-term rewards. And the way that we would introduce this is by introducing a discounting factor here, gamma. All right, so by introducing this factor gamma, we can weight the fact that future rewards might be less important to us than current rewards. And so this parameter gamma is a parameter that is less than or equal to 1. In the limit that this discount factor is equal to 1, this agent is very far-sighted. It cares about rewards all the way into the future. And so we would say that the agent does not discount at all. If this discount factor goes to 0, then we would say that the agent is fully myopic. It only cares about the next reward. And so again, this is something that we can dial depending on how nearsighted or farsighted we think our agent should or might be. Okay. But the one thing that I want to point out here is that when we write the return like this, we can factor out gamma, and we can write the return at time t in terms of the return at time t plus 1. And so we can define a recursive relationship between the return at successive time points. And we're going to take advantage of this relationship in a moment. And so I'm going to set this aside for right now. Okay, so this is the quantity that we ultimately want to maximize, is this return. The problem is that this return isn't something that's known to the agent. So the return represents actual future rewards, and the agent doesn't know what rewards it will be getting in the future. So instead, we can compute the expected future rewards, given that we're starting in a particular state and following a particular policy. So to sketch this out, I want to think just about one time step in the future. So let's say that we want to compute the reward we expect to get on the next time step. The way I'm going to write that is as the expectation over the reward at time t plus 1, given that we're following our policy pi, and given that we're starting in a particular state s. And so the way that we can define this is in terms of the reward that we would get given that we start in s and take an action a to state s prime. Now, a and s prime are things that we don't know, and so we're going to average over those. So we can weight this reward function by the dynamics of the environment, which tell us how likely it is to move from state s to state s prime if we take the action a. And given that we don't know this state s prime, we can sum over this. Now we can weight all of this by the probability that we would take an action A from state S. Again, we don't know action A, so we can sum over this. And in this way, we can compute the expected reward that we would get one time step into the future. All right, we're also going to use this relationship, so I'm going to set this below for right now. Okay, so now I'm going to define what we've been calling the value function, the state value function, starting in state S, following policy pi, and I'm going to define that as the expected value of the return, right, averaged over our policy and assuming we're starting in state S. So you can think of this as a prediction of rewards to come, right? We're computing the expectation of the return in the future. Now we know that this return can be expressed in terms of the return at time t plus 1, so I've just substituted that in here. And now we can start breaking apart this expectation value. So if we focus on this first term here, we already computed the expectation of this first term. This is down below, so I'm going to substitute that back in. And now we can move to this second term here, and we pull out a factor of gamma, and the expectation of this return at time t plus 1 is defined with respect to the state that we would arrive at time t plus 1, which is state s prime. And now when we write it like this, we can see that this term is this same value function evaluated at state s prime. So what we've done is we've written the value function with respect to state S in terms of the value with respect to state S prime. So this defines a recursive relationship between the value function at different states. And this is what's referred to as the Bellman equation for the state value function. Okay, so we can define this relationship for our state value function, V, or we can also define this with respect to what we've been calling to Q, which is what we would call an action value function, the value of taking a particular action from a given state. Okay, now there are different types of methods within the field of reinforcement learning that have been used to identify optimal policies and state and action value functions. And so there are different classes of these approaches. So there are methods coming from the field of dynamic programming that assume knowledge of this model of the environment. So we know the dynamics of the environment, and we know this reward function, and we want to learn optimal value functions and policies via bootstrapping. There are also methods coming from Monte Carlo methods that try to estimate these optimal value functions and derive optimal policies from sampling and from simulated experiences. And so these have been two different branches that have really informed and influenced, defined the field of reinforcement learning. And there have been a class of algorithms that have combined aspects of both of these called temporal difference methods. And so many of you may have heard of these, but these temporal difference methods leverage some of the advantages of each of these two types of approaches. And these methods focus on learning from experience in an online fashion using bootstrapping, so updating an estimate from another estimate. And so we're going to walk through some of these temporal difference methods. So the idea behind temporal difference methods is that you improve your estimate of value incrementally and iteratively through your own experiences. And the basic update rule that's used in most temporal difference methods can be written in the following way. So we want to construct a new estimate based on our previous estimate, and we want to update this estimate given some error that we would get by comparing this estimate to some target that we care about. And so this is some measure of error that we're going to weight by some step size. This tells us how much we're going to update our old estimate based on how much it deviated from this target. So this new estimate we can write as the estimate of our value function of value at time t plus 1 with respect to a specific state. And we're going to be writing that by updating our estimate of that same value function one time step earlier. And we're going to do that using this error measure here, and we're going to weight it by this step size alpha. This is often called the learning rate in reinforcement learning. And so here, the target that we really care about is this return, the expected long-term reward. And so we're going to be comparing this return to our old estimate. Now the problem is, again, this return is something that the agent doesn't know. This is the sum of all rewards into the future. And so what temporal difference methods do is they replace the actual return with an estimate of that return. And so we can approximate this return using an estimate. You can see the parallel of this term here with what we derived from Bellman's equation earlier. So we're going to approximate this return based on the reward we got plus gamma times the value function evaluated at the state that we moved to get that reward. So in this way, we can incrementally update our estimate of value based on our estimate of value. Okay, so this defines our update rule for a state value function when we would move from state S to state S prime and collect a reward R. We can write down an analogous update rule for our action value function, and this update rule forms the basis of methods that you might know like Q-learning or SARSA. And both of these are defined in terms of what we would call a prediction error. That's an error between the reward we expected or predicted to get and a reward that we actually got. So everything that I've told you so far assumes that we can update our estimate of value at a particular state, given that we visited that state. So we can only update our estimate of value if we visit, for the states that we visited. If we want to update estimates of value at other states, we can introduce something called an eligibility trace. And so to do that, we can multiply this update by what we would call the eligibility of state S. And so the eligibility of state S allows us to update other states that we aren't currently visiting, but that we have visited in the past. And so we can write this eligibility if we are at a state that we're not visiting right now, we can write this eligibility as a decaying function of time, where we're decaying this based on what we would call a trace decay parameter, lambda. So this parameter lambda is another parameter that goes between 0 and 1 and tells us how much our eligibility will decay over time when we don't visit a particular state. So if this trace decay parameter takes a value of 0, that means that only the current state can be updated. If we crank this trace decay parameter all the way to 1, that means the eligibility of a particular state falls by a factor gamma each time step. So whenever we're not visiting that state, the eligibility of that state decays. When we visit a state, we then update the eligibility of that state incrementally. So what this allows us to do is, as we visit states, we update the eligibility of that state, and as time goes on and we stop visiting that state, the eligibility of that state will decay. So the way that we can think about this, if we're looking at the eligibility of a particular state S, we can look at how that eligibility would change as we visit that particular state. And so if these are visits to a particular state on the x-axis here, you can see that the eligibility of that state will increase every time we visit that state and decay in between visits. Okay, so what does this ultimately mean? What does this allow us to do? When we add this eligibility onto our update rule here, this allows us to keep track of states that we visited in the past and update the value associated with those states. So let's say that we're moving in this 2D grid that we've been thinking about here, and we walk through this grid and stumble upon this particular reward. If we have a trace decay parameter of 0, which means that we don't have this eligibility term, we're only updating our current state, then that means we only update information about the state that just preceded our visit to this rewarding spot. We learn nothing about the rest of this trajectory that led us to that point. Alternatively, if we make this trace decay parameter greater than 0, then we update states in proportion to how far into the past we visited them. So more recent states are updated more strongly than states into the past. So in this way, we can incorporate information about the specific path that we might have taken to get a reward, and we can think about how experiences in the past might impact the rewards that we're getting right now in the present. So with this combination of value functions and policies, we can understand how animals might incrementally update their behavior based on their own experience. So as they gather rewards or punishments from the environment, they can use this information to update an internal estimate of how good or bad it is to be in a particular part of the environment and learn to change their behavior accordingly. And in the problem set that you all will be working on in a little bit, you'll be thinking about how to actually implement some of these types of algorithms to model and simulate the behavior of an agent that's learning based on its experiences. So with that, I think I'm going to have us break. I'm happy to take any questions that you might have, but we're going to come back at 2:40, and then we're going to start working on this problem set. All right, thanks so much.
Place cells.
Then, in principle, without having this model that tells you, this is the important feature of the world, rather than the specific classified location, it's actually certain features. If you don't have that information, you just have that error, then the algorithms that you would require you to relearn everything. And so you have to build that into the knowledge that animals have about their state space and how to pattern actions to so there are different ways that you build that knowledge. One way, so if you represent the state of the world as individual locations in the space and time, if you represent the state of the world as features, then you don't suffer from this problem because you're heavily learning to get features. But then that you sort of subsumes that part of the problem and saying the animal knows those features. So you have to sort of have a way to do how you build up that feature map and then you tether it to the learner. So you have to think about both of those pieces. And you could gloss over that and assume the animal knows, oh, the door is, I know what a door is, and I know that's different from this pole. But that's an assumption. You can either build in the algorithm, or you could describe how the animal builds up that model of the relevant feature from the so you have to keep building that knowledge into the framework so you can then exploit that knowledge when the knowledge comes.
Right, but that's the thing. So, is the environment really, from a very novice perspective, the environment really isn't changing much. It's only the location of the platform. Say when you don't change visual cues or anything, so it's only the location of the platform that is changed. But the rat now knows that like after one random trial, he knows.
I'm misunderstanding what you asked.
Yeah, so that's exactly the point. That like after one random trial, once he already knows how to solve Morris motor maze, after one random trial to a new location, he will directly start going there.
So there you're asking how you build knowledge of the task itself.
Exactly.
Yes, and so basically in these sorts of algorithms, one has to think about what is the knowledge of the task, and if it's knowledge about the structure of the task, and somehow that needs to be known as well. What are the rules that are underlying this? So the rule is that there is a platform, there is a platform, and will be in a particular location. So once I find it, I know to color it to the location.
Yes, exactly.
This environment. Right. So then you have to think about learning this rule structure. That's a difficult problem, and you have to ask how much of that is known a priori, and how much of that structure has to be learned from experience. How do you actually build that knowledge? It's a difficult problem, but it's basically, do you assume that the rat knows what objects are, and once it encounters an object, it can place that object in some space of knowledge. Those are the types of assumptions that you have to start building in, but it's an important question to think about how much are animals learning about the specifics of this setup versus learning about the rules of the underlying task. They're two different active areas of knowledge.
Right, because the way I think about it is, say for example, using learning to learn kind of paradigms where people think in terms of the neural state space, where once you have learned a task, you sort of have learned the dynamics of the task in your neural state space, and you start exploiting that dynamics. Even if little things change in your task, like say the actual identity of the features change, but you still know on what basis to choose the new set of pictures from the new set of pictures, just based on the fact that your neurons in whatever part of your cortex is now like entrained to a particular kind of dynamics.
If you're thinking that way, you should build a manifest, right? You're building it as a manifest.
Right.
And then in some sense, you're implying that manifest contains this past knowledge.
Right. And that'd be tied to the reinforcement learning idea that
think the piece that's not obvious to me is exactly what about that manifold dynamic is representing ambiguity. So, but I think that you can say that a way that a rule could be implemented is in this sort of manifold dynamic. And so then there's the question, how do you build a manifold that holds the rule? And if you, so, which is a different type of question, but given that you then have this manifold, you can say, I've learned that this somehow contains myself, so I tether everything to that. But in some sense, part of the question is still being pushed off in terms of how you can move into a manifold.
Right.
But in that way, you could start to,
Right. Exactly.
it's an interesting challenge, but it is, it's not clear. I mean, I think it's, yeah, it's
Is there a
not.
mathematical way to define that?
Yeah.
Because you're building a giant lookup table, is what it is.
This is entirely.
Yes.
What
Including deep learning is, I think,
is a giant, yeah, is a giant. And I think there are animals learning much smarter than search and exhaustive. And so one of the things I think is really exciting is to think about how animals can exploit other types of awareness. So the first part of the talk talked about exploiting, you can think about exploiting other types of awareness that would allow you to compress this massive lookup table into some more informative task-based structure. So rather than having to search through this tiny space, you represent the world in compact ways. You know something about who you created, how the world is organized, how you create it. That's a very open table. It's a really cool and exciting place. So I think the exhaustive lookup tables are impossible it's very hard to link those directly.
The worst part of the is that these constraints that you're putting are pretty tough in the sense that you're assuming that the brain is trying to do it in a constrained way. Does not do that. The only constraint is evolution. And how do you build that? What's the kind of framework you build up?
It's a very good question. So, I mean, one way that evolution comes into play is in terms of the type of structures that you learn. So, I mean, the argument that we made in the first part of the lecture are all innate in evolution. The visual system is adapted to statistics and natural symbols are constant, on and that. And so, through evolution, our visual systems are exposed, are adapted to these statistics as much as we can possibly understand that. But it doesn't necessarily talk about the dynamics of what happens in development and learning and behavior. And so it's going somewhere with that the question now is where we stop there. So we could, the role that evolution could play in this, I think in some sense determines how much of a strategy is shared and how much of a shared is practical. So one thing that we think about a lot is whether insects like the flies, who have gone through many evolutionary might have some smart structures as part of identity that other animals don't know. So you can think about how you might build, sort of enforce sort of smart strategies through evolution that you ask the semi-smart or you represent
generate a path that is highly scientific to get to a point, right? But the thing is, now I don't, I didn't even know that this action was possible before I encountered this community reference state, and that's basically because of the explosion of the things that you can learn.
Yeah. So I mean, one way that we think about that explosion in terms of smart parameterization that actually is. So it's not as though you can take any action. Physicists are saying an action algorithm, and then there's an energetic and so we can already use that knowledge to constrain the way we define actions. And so we can.
But without being, if you didn't have the power, right, at this stage, describe all the actions possible, none of this is possible, right? Like you can't learn anything, you can't build up.
Anyway, this is all, right in the sense that it's all built on the assumption that you find this requirement of binary action. And in discrete spaces like this, that blows up as the number of states. But if you want to parameterize this, and I think we've been working on the problem set, it doesn't seem to display but rather that
concept that you can use that, you know, if you have constraint the optimizer finding rate for both the constraint and the unified get this improvement. How can you ask how can you prove that if you have a pointer overloading?
Yes, okay, so the way to work this out is to maximize, so if you write down a Lagrange that includes the entropy, so negative several negative Lagrange multiplier times your constraint. Your constraint here, you're shifting them with the sum of the probabilities. So adding in a new firing rate, for example, so you want to add a radius that one is between the average response. If you want to constrain some of our instead of constrain that radius. So the input, so using the Lagrange multiplier can solve for the algorithm. Then you can find and get back into the data. Now the happy answer is trying to figure this out, but that's really much better. You can find that works out in three simple fluctuations. Jonathan, Phil, will have some questions as it works this out.
I have some at the back end.
Are we going to go through the derivation?
I ended up removing it. Let me see.
So this is the basic way that you could set that up. So if you write down the Lagrange max, this is just for the first and you just don't have that constraint, which is some of you can work here and get back to your probability. We actually want to use the constraint. The constraint means it's all the same. You'll have no because you have two different Lagrange. And you will solve that as well. And you will put that in.
Solving the mechanics.
Yeah, and for me it was also when you got to
Thank you very much.
Of course, of course. Oh, is it already 2:40? Shoot, okay. I would, where are you sitting? And I'll come over and, somewhere in the back. Okay. Come grab me. I'll just introduce the problem set and then we'll be working. I'm happy to answer your questions. Of course, of course. Okay, everybody, we're going to get started again. So if you want to take your seats. Okay, so we spent some time introducing normative frameworks for thinking about sensory coding, inference, and action selection. And so now we're going to work through a problem set that tries to sketch out these different frameworks in the context of one common problem, which is a foraging problem. So the problem set you can find at this link here. And so for those of you who missed the Wi-Fi code earlier, here it is. You can navigate here to get the problem set, and there's a worksheet that you should all have that accompanies that problem set. If you don't have that, come find me. I'm just going to walk you through what the problem set looks like, and then I'll put this back up so that you can navigate to that. Okay. So when you find the problem set, it will look something like this.
Your worksheet should look something like this. We've introduced these normative frameworks for sensory coding, inference, and action selection, and so you'll find sections of the problem set addressing each of these. So there will be a section at the beginning that sets up the problem, followed by sections that address or explore each of these different topics. So if we looked, for example, in the sensory coding section, you'll see a series of problems that will ask you to work through different things on pen and paper. In some cases, it'll ask you to sketch something, so this is where you'll use a worksheet, so you can sketch out whatever it asks you to sketch out. And then you'll see that this is followed by starred problems. So I want you all to start by working on these non-starred problems first. These are problems that you can do on pen and paper, you can do directly on the worksheet, and then after you've done all the non-starred problems for all 3 sections, then come back and tackle the starred problems. These starred problems are more involved, and in some cases involve coding and simulation. So you might see problems that ask you to numerically optimize something or find something, and so for that, you can do this computationally. If you want, Sashank has developed code and put it online at this. You can navigate to it at this same link. There's a link to both MATLAB and Python code that works through these problems and can help you develop intuition and can simulate some of the things that you will have worked out analytically. So I'd encourage you to check that out. In another hour or so, we'll come back and go over the problem set and give some sort of forward-looking thoughts. So with that, I'll just navigate back to, actually, this is the link that you need. So if you just follow this link, you'll find links to the problem set, the worksheet, and all of the code. All of the TAs will be here to help you through this, so just raise your hands if you have any questions, and we'll be wandering around. All right, thanks. Let me put up the beginning of it on one screen. I don't know how to put it on one screen. I could put it on both screens, which would be fine. Yeah, it is really, it's dark. I'll come figure out how. That's a great, let me try.
it will sort of move whatever's on one side and actually separate it. And it creates exactly. And that I used to use like ant forever, and then you can do it with these systems. So thank you. I really love it. That's the hope is that it's hard to tackle all of that. It's hopefully we can follow it. Thank you. I really appreciate that. My hope is that it's been an ongoing process. They will. I'll put them up, and just after I'm done today, I'll post them all. I'm saying that that is so that is super interesting. I think it's something that we're we actually is in terms of linking information to the if you have some issues with primary information and different how do you use both of it? How do you balance those potential implications and that really important to keep up So, in terms of curiosity for the inspiration, really focus. It's an open question. So, I think about the national reward setting that we do. In a setting where artists, what is it described? Is it finding really with some and how do you just watch the permanent box? What is what is it? And how can that be combined? What is it? I think it's so we're trying to sort of formalize like getting our hands on the problem sometimes and how to actually implement it as no worries. My brain is moving all day, so. This is a very good point. So in some sense, in many cases, what not So me just put this up here. Is that going to? There's the link. Okay. So no more power strips. Let me. Where are the power strips? Are they at the table? Okay. I haven't either. What was that? 15 minutes. 1-5. Yeah. Let me try to find. I'll ask if there are more power strips. Where's the table that's for that one? In the back corner. Okay. If not, I mean, is there a power strip up here?
That's awesome. One thing I was going to ask you, but that we can chat about now.
bee would make sense of this landscape, how it would distinguish whether it's in the forest or the field, and how it would change its behavior based on rewards that it got for being in the forest or for being in the field. So I want to walk through a couple elements of this problem just to give you a sense of where these ideas can take us and some of the things that, that were starred extra problems that you may or may not have gotten to. Okay, so we started off this problem set asking how you would build a good detector for encoding different distributions of frequencies, and I asked you to draw the nonlinearities that might be best for encoding the distribution in the field versus the forest, and those nonlinearities might look something like this, but you could formally derive those using the approaches that we laid out at the beginning of this tutorial by working backwards from the distribution of spike counts that you might want. So if you want to maximize entropy at the output, you can work backwards from this maximum entropy distribution to find out how you have to partition this input distribution into equal chunks. All right, and so that's one way that you could derive this nonlinearity. And then I asked you to think about what this would imply if the bee were to use this nonlinearity in the wrong context. So let's say it's adapted to the forest, and then it suddenly finds itself in the field. What happens? And so to look at that, we can project now this distribution of frequencies in the field through this same blue nonlinearity. And so if we do that, what we see is that a bulk of this distribution gets mapped onto just a single spike count. So what we see is that this distribution over here has very low entropy. Essentially, we lose all of the information that we might have formerly had about distinguishing different frequencies if we use the wrong detector. All right, so this is a big challenge if we want to think about actually dynamically adapting these detectors. And so one of the problems that you were asked to think about would be what would happen if the bee were moving between the forest and the field, and how would it infer that it's in one or the other, and how would it use that information to adapt these tuning curves. But already you can start to see a logical problem here that if you're adapted for the wrong context, you lose the ability to learn anything about a new context, and it makes it very hard to infer that something has changed, and it makes it hard to adapt to that change. So this is a problem that we've been interested in thinking about, and I alluded to this a little bit earlier in working through this sketch of Bayesian inference in the lecture. So I wanted to take you through how I'm thinking about this problem in a slightly different context. So let's say we revisit this environment that we're trying to navigate through, and we just represent the forest and the field as gray and white chunks. And we have our bee sort of flying straight through the forest and the field, so it's encountering different patches of one or the other, and it needs to infer whether it's in the forest or whether it's in the field. So you built up a model of how it could make this inference if it had direct access to these signals here. And the problem we've been wanting to think about is what happens if the bee doesn't have access to these signals, but it has access to these impoverished spike counts, so the output of this nonlinearity here. And if we move away from trying to design these nonlinearities to maximize information about the current context we're in, and rather think about making inferences about changes in context, we get qualitatively different types of solutions. So I wanted to give you a flavor of what that looks like. So let's consider this problem where the bee is moving in time through different contexts here. And I want to compare the strategies that we would get if we're trying to directly preserve information about frequency. This is analogous to what we worked out at the beginning of the tutorial. So we care about the frequency itself versus we care about preserving information about the underlying context. And the solutions that we would get, depending on these two different objectives, are qualitatively different. Okay, so in both cases, we're trying to infer changes in this distribution of frequency, and we're trying to do that using the output of these tuning curves that map frequency onto some firing rate or some spike counts. And so here we're going to now optimize our tuning curves in two different ways. This is the classic way that we would have worked out in the beginning of the lecture. This is a slightly different way where we care about preserving this contextual information. And so if we look at how these evolve in time as you're switching between different contexts, you see that both of these nonlinearities dynamically adapt, but they do so in qualitatively different ways. So the nonlinearity on the left here maintains a constant slope and just scoots left and right, whereas the nonlinearity on the right does this sort of inchwormy sort of thing. And so this gives rise to very different measures of performance. So if we wanted to actually measure how well we can decode, whether we're in the, decode this frequency information here, we can compare these two different strategies, and we find that they produce very different errors. So I'm gonna play this video for you again. And what you see is that even though we've optimized this nonlinearity for preserving information about frequency, when we actually go to decode that frequency information, this system has very high errors. And that's because it's very slow to detect and respond to changes in the environment. So this sort of identifies trade-offs that can arise when we're trying to balance these competing goals of preserving information about things that we care about in the environment and inferring changes in the underlying distributions of those features. And so we can see these trade-offs arising in how well these systems perform in steady state versus in how they dynamically respond to these changes. And so this is a problem that we've been interested in working on and sort of bridges together these ideas of efficient coding and these ideas of Bayesian inference and tells us how we could think about dynamically adapting some of the strategies that I told you about earlier to deal with changing environmental contexts. Okay, so this was beyond the scope of the problem set, but this is sort of what I had in mind in sort of pushing you to think about some of the trade-offs that might arise when you're trying to balance these different competing objectives. So from building on this inference piece, we moved to think about how this bee would actually learn from its experiences based on acquiring rewards collected from the flowers that it had encountered. And this is a video that Sashank made, and the code is available online, so you can simulate this yourself. But here on the left, we're looking at a bee in the field. And you can see it's, when I play this video, this is its value function changing over time based on its experience. You can see how it would reorient depending on its change in this value estimate from one time step to the next. Okay, so here you can see the bee learning to navigate in the field, and over time, you'll see that it tends to spend more time in this orange area where it's likely to receive more rewards. In the forest, you can see that the bee learns to navigate towards these bluer patches where it finds more rewarding flowers. And we can build up these types of learning algorithms. So we used a different approach in the problem set that I gave you than what we worked out in the lecture. So rather than treating this as a discrete space where there are discrete states and discrete actions, we thought about a continuous set of states and a continuous set of actions, and we parameterized those, and we parameterized the value over those states. We used a very simple parameterization. We were just taking this to be a linear function with a variable slope, but this is something that you can build in a much more sophisticated way using sort of a beefier version of function approximation. And this would allow you to get sort of a richer approximation of value here that can create a more flexible model. It comes at the cost of additional parameters. So I hope this gave you some intuition about how you could go about sort of constructing these types of learning algorithms. I'd encourage you to play around with the code if you didn't get there today, just to get an intuition for, you worked out on your worksheet sort of one time step of an update, and this will give you more intuition about how those updates are chained together to change the behavior over a longer period of time. Okay, so I just want to, I have this twice for you. I was so excited about it, I wanted to make sure you guys saw it a couple times. I thought this was really cool. This is going to be my screensaver from now on. Okay. So before we end, I just want to step back and sort of reflect on the set of problems that we tried to tackle today. So I tried to give you a broad overview of different normative approaches that have been used to think about sensory coding, inference, and action selection. And the broad idea behind all of these approaches is that there is structure in the world. The world in which we live is lawful. Animals and brains can exploit this lawfulness to their own advantage, and they can do that in many different ways. So we talked about this in the context of how you could remove redundancy from the world around you, how you could combat noise, how you could reduce uncertainty, and how you could make predictions about the future. And so we treated these as sort of 3 different lecture modules, and even in your problem set, you tackled these in 3 different sections. So a section on sensory coding, a section on inference, a section on action selection. In reality, these are all coupled. These all support and constrain one another, and I think a really exciting area for future theoretical work is to think about how these impact one another. I think there's a lot of room for development here to understand how bottlenecks on the early sensory side can impact all of these downstream computations, and in parallel, how we could think about how these later types of stages might exploit the same types of structures that we talked about when we were dealing with sensory coding. And so I hope that all of you will start working in this field so that we can solve these problems. But in general, I think there's a lot of exciting work to do here, and I hope this gave an introduction to some of that. Thank you all for being here. This was a ton of fun. Please come and talk to me if you have any more questions. And before we end, I just want to say a huge thanks to all the TAs. They did an incredible amount of work for this. It was really awesome to work with them. So please ask them questions as well if you have any. Thank you all. And you're free to go.